So in this case, we need to have a continuation as we are to consider our DC machines, the speed control. This is a typical question that we are going to have and see some of the other terms that we might be given, which are important for you to know as you are to consider your exam answering. There we are given on our question, a DC series motor. Take note. This is the original condition. Operating at full load rotates at. Then after that, the speed of the motor changed to this 1,250 revs per minute by connecting. Take note. What is it that was connected? A diverter resistance across the field course. If you consider the introduction, the first part I considered where the diverter resistor is and how do you calculate the resistance of the armature circuit. You must work on that. Then we are given the series field resistance. Calculate the value of the diverter resistance, which is fine. We need to calculate the value of what? The diverter resistor. But if the current, this is the most important, let's take here. If the current drawn from the supply remains unchanged, there's something here. The current that is drawn from the supply. Remember, there are two conditions as you have to consider your speed. You'll be having two conditions. Original and that of the final. Original condition and considering your final condition. Remember, we had this one. If you are to consider, they are simply saying current drawn from the supply. When it is original, you're going to use 1. Final, you're going to use 2. It's the same. It did not change. So that is current from the supply is equal for the first condition, which is your original, is equal to that of the final condition. That is what they're simply telling you there. Same current. Then we have to consider another part. Then they say it here, assume that the field system is unsaturated. Okay, meaning just use those normal considerations of our formulas as the torque is proportional to your speed, this and that. But there is another statement here. They are saying, and that the resistive voltage drop is negligible, which is negligible. That is, it can be neglected. Too small to have an effect. Too small to have an effect. Remember, when something that is not having an effect cannot be considered as part of your circuit. The resistive voltage drop, what is it that you consider as the resistive voltage drop? The voltage drop is where the resistance is, where if you are to consider, let's say, when you calculate E, remember E is going to be equal to what? V minus what? Armature current and the resistance of the armature circuit. But they're saying the voltage drop there, that resistive voltage drop is negligible. That means it can be removed from our circuit as if it's not there. It's too small that you can even neglect it. So simply E is going to be equal to what? To V in that condition. When we are to consider this, in the same sense, if E is equal to V, we are going to notice that E2 will have the same effect again because this is not considered. So E2 will be equal to V again. So if E1 is equal to V, E2 is equal to V. Therefore, what can we say? Therefore, E1 is equal to E2. The generated EMF 1 is equal to the generated EMF of the second, which is the final condition. Because we're going to have the same answer there. Because there's nothing there. So the terminal voltage is your E. The terminal voltage is your E. So if your terminal voltage and E is the same, it means E1 is equal to E2. So you're not going to consider that part of calculations. You just need to know this. It's a part that you need to consider when it is an exam condition. You see that there's no need for even those calculations there. That is what they are saying. Negligible. Too small to have an effect. All right, so that is it, guys. These are some of the terms that I just wanted you to understand. But as you consider, as we had before, nothing is going to change. Everything is remaining as it is. A DC series motor, your original condition, that's a series motor. So that's we're going to have our field connected to the armature. Field to the armature, that is a series. So according to this question that we are given, they are saying it is operating at full load and rotates at the speed of 1,100. So meaning we are given at full load the speed 1,100 revs per minute. The speed of the motor is changed too. So the final condition, we are given the speed there. It is now at 1,250 revs per minute. This was caused by what? Connecting a diverter across the field. Remember this of the diverter. So meaning say the final condition, we are going to have a diverter resistor connected to the what? To the field. So this is the part of the field. We're going to have our diverter resistor like this. All right. So that's the condition there. Remember, it is connected in parallel, this additional resistor, which is given a special name called what? The diverter resistor. We are not having the value. We are supposed to calculate its value. So we're just going to leave it like this. All right, having what? At the terminals, we do understand that the voltage there is going to be the same. But are we given that? We are not given. So let's just have our V. And also, let's just have our V. Remember, the generated EMF, which is actually your back EMF here, as we considered E1 is equivalent to what? To E2. All these, they're just the same. E1 is equal to E2. It is also equal to V in that condition. All right. So if we have any of these, if let's say it is calculated, then we can use it. But let's see, according to our diagram. So they also gave us, let's consider these resistances here. The series field has a resistance of 0.15, the part of the series field. Resistance of the field is given 0.15. That's 0.15 ohms, which is not going to change even here. The field, that's 0.15 ohms. So that is it, guys. According to the information that we had, and considering this, the load current, because here we're going to have our load current entering into here, having your series field current into what? This is the same, which is your armature current. This is the same that we're going to have here, because we said, these current, they're the same. The loads current, they're the same. So meaning to say, the IE1 that we have there is the same as the load current 2 that we're going to have here, which is entering here, branching to give us the current of what? Of the field. And that of what? The diverter resistor. So you're going to have the current there across. All these, like I explained, guys, they're going to branch again. They end up going to the armature. So this is the current that will give us armature, which is the same as that one that we had before here. The same thing. Kirchhoff's law. You can use that. So this is it, guys. Let's consider our calculations. These powers, guys, you just have to draw a diagram, and also the resistance of the armature. There's nothing here that we are told about the resistance of the armature. Resistance of the armature. All right. Remember, this part is where the resistive voltage drop is what? Negligible. which affected that it has no effect. So the resistance of the armature, there it is into that has been taken into. That is why they are not even bothering to give us that value. So no problem. Let's see. This is what we are given according to our diagram and information. So those terms, they're very, very important to understand. So with what we had and all these conditions, the question is for you to calculate this RD, the diverter resistor. How are we going to obtain that? What can we do? So as long as to deal with the speed control, the steps as we had, I said, you need the diagrams as we had here. This is part of your solution, the diagrams. Then after, the second step is to consider your main speed control formula to see what is it that I'm supposed to calculate. You might be saying, what if I just use the diagram direct and calculate this, because does it affect? Okay, this is what you're going to see. I want you to see what was going to happen, because you have a current divider rule. Remember, I told you guys in parallel to calculate ID, we're supposed to use the current divider rule, opposite resistor on top, meaning to say we're going to have RF over what? The sum of these two resistors, RD plus RF, times the current which is entering there. So we can use, because we said the load current 1 is the same as the load current 2 at the end. This is the same here that is armature current 2. Same, this is the same thing Kirchhoff's law, guys, tells us. Here we are told that this load current is unchanged. It's not about Kirchhoff's, this one. We are not using Kirchhoff's here. The Kirchhoff's is playing here to say the current entered. So it is one branching into this branch, another one into this branch. Those currents are the ones that are still branching to give us this one, the total. So the total that we had is the same total that is here. So that is why we are saying this load current is equal to the armature current. But these two being equal, it's a given condition, this one. It's a condition that we are given. Please do not confuse that. So meaning to say on this part, you're going to multiply any of these. Is it the load current? 1, is it the 2? Is it the armature current? Definitely you do not have this. This load current, this, but the armature current, there's a possibility of us having, and also the armature current, remember, it is also part of our circuit when you consider those generated EMF. So it is going to be best for you to write in terms of armature current, and also the armature current plays a role when you are to use the condition of the torque, if you are to consider that. So in this case, you can use what? The armature current instead. You can use any of these. But what is it? The higher possibilities of our questions is the armature current. And with this, guys, we're going to see that, okay, still that I need this armature current, because I have this one. Remember, we need, like, if you're to find ID. So you can make the subject, then RD, you make the subject there. ID, do you have it? No. Do you have even this field? You do not have. So using this, you're going to see that even if I am to use this calculation, the armature current is needed. So there is no way, guys. We need to go back to that part of our speed, the main speed equation. So that is what I was explaining, that no matter the way that you want to answer these questions, the steps that they specify there are the ones that you're supposed to follow. So the second step, remember, is our main speed formula from the main speed formula. Main speed formula. What are we given? That is E1 over E2 must be equal to, in terms of the flux, or is it in terms of the currents? Are we having flux? No. So we're going to write in terms of what? The current. So N1, field current 1, N2, field current 2. Remember, this can be given in terms of what? In terms of the flux. It can be flux 1, can be flux 2, but we can't use that because we're not having that, and we're not even told about that. So we can at least work with what? Field current. There are possibilities of calculating that field current. So this is what we need. So using this, remember you're supposed to circle like, what is it that you're going to need from this, which will help us here to calculate the RD, which will help us to calculate RD. So if we think of RD, we can think of calculations like, where can we have it? Where can we actually have it? The field current, it consists of RD when you calculate it, just like how I was calculating here. Because guys, which part are you supposed to calculate? You have to ask yourself that. So we saw that ID, it consists of RD, but ID is not part of what? Is not part of this formula. What is part of this formula is this, IF2. Can we use that IF2? Yes, just like how I wrote the formula for for ID, IF2 is supposed to be equal to what? From your current divider rule, opposite resistor on top. So it is supposed to be RD over the sum RD plus RF times what? Like I said, you can use any of these currents, but the possibility or the higher possibility is working with what? The armature current than to work with what? Than to work with the load. We can work with armature current. We can work with anything. And that armature current or the load here is the same here. So you can even get it to IF1 or armature current 1, anything that you are going to have here. So this can be I load 1, this can be I load 2, anything that is equivalent to that. So we will see. But as we are to consider our calculations, here we are stuck because we do not have this. Where is it found? At least we can see from our main speed formula, it is there. So this is the part that you are supposed to circle. This is the part that you're supposed to circle. And say, if you have it, then it's going to help you to calculate that. So this is the part that we are supposed to circle. And where are we going to have it? Are we having any of these? Even IF1. All right, let's consider our calculations. The main part is that you cannot calculate this E1. You're not given. But remember your relationship here that we said E1 is equal to E2 is equal to V. So meaning say these two, they can cancel here from your main. This one and this one is the same. So it's going to be 1/1. The speeds, they are there. So let's substitute and see what's going to happen here because these speeds, they are there. All right, let's substitute. From this, we are going to substitute. This is same as 1/1. We are on the main speed, guys. 1/1 is equal to what? N1, we have it, 1,100 times the field. We cannot calculate that here because we do not have V. Remember, you're supposed to have your field to say, okay, this is this voltage that we are given. Even if you are given the load current there is nothing that you can consider. So we do not have that. So let's just write as it is. So this is the field 1. N2, we have it, 1250 times field 2. You are at a consideration like this and you be asking yourself, how am I going to go about this? We have got 2 unknown. So we can write 1 in terms of another one. Okay, we can write 1 in terms of another one. That is what we can see here. So let's cross multiply. 1 times this is going to be 1250 IF2 is equal to 1 times this is going to be 100 IF1. So it's either I can write IF1 in terms of IF2 or IF2 in terms of IF1. It's up to you. So, okay, let's just divide this by 1,250 here. 1,250. So let's see what's going to happen. So we are going to obtain a field current 2 in terms of field current 1. According to this, which was going to be 0.88. If you round off, 0.88 times the field current 1. So you can say this is an equation that we have formed. let's just say equation 1. We have IF2 in terms of what? IF1. Let's go back to that IF2 here that we had here and try to analyze again. Analyze again. Is there going to be a possibility of having armature current? Because what we need is this RD, this one. And you can even call this, let RD be X. It's up to you guys. It's up to you. You can just use the RD as it is. So you're asking yourself, like, from this armature current, because this one is given now in terms of what? It is given in terms of IF1. We have it here. It is given in terms of IF1. So your question now is that it's here now on the armature current because it cannot be calculated. But do we have anything equal to that which is IF1? Because this one, remember, it's in what? It's in terms of IF1. So you're supposed to think of the armature current too. Can it be written also in terms of IF1 so that at least one of these, if it is written in terms of 1, it can cancel. Just like what we had here. If it is one thing, like guys, like what we saw here to say E1 and E2, because it is just like you're having E1 over E1. They are the same, they can cancel. So if we have IF1 here, then we can cancel. So the question is, where can we obtain it? Let's go back here. The armature current 2 is the same as the load current 2, which is the same as the load current 1. If it is the same as the load current 1, then we have it, because the load current 1 from the original diagram here, from our original condition, the load current 1 is equal to the field current. It is also equal to the armature current 1. It's a series connection. The current is the same. So by knowing this, it means the load current 1 is equal to what? Armature current 1. The load current 1 is equal to what? The field current 1. So we have the field current 1 there. Since load current 1 is equal to the field current 1 here. We got this. Since we have this, therefore we are going to make a substitution here on that one. Therefore, we are going to have our formula as IF2 is equal to RD over RD plus RF times what we need, because this one is written, remember, in terms of what? IF1. So this, let it also be in terms of IF1. So to finalize, before you see your question is very, very wrong, because you have to consider the condition. So you see this type of a question, guys, you have to focus. Now they want to test your mathematical skills in terms of interpreting your question, change of subject or formula, your mathematics N4 there. That is why they are testing you now. So I have this in terms, IF2 in terms of IF1. So guys, RD can be calculated. Whether you call RDX, whether you call it Y, whatever that you call it, it can be calculated. I'm just going to use it as RD as it is so that we do not have confusion. All right, so IF2, as we had it here, remember in terms of IF1, it is 0.88 IF1. 0.88 IF1. So you can use it like that. You can use it as it is. Like this. Okay, let me take it so that I do not confuse you guys. IF2 as it is. 0.88 IF1. We have a substitute. It is written in terms of IF1, remember. So this is equal to RD. which is the one that you need. Remember, RD is the one that you're supposed to calculate. You're supposed to calculate this, remember. So there's no substitute there. We're just going to write as it is, or you can use X there, like I explained before. So this is RD again plus RF, which is this one, 0.15. We have it. 0.15 times what? We are supposed to use the load current 2, but the load current 2 is same as the load current 1, is same as armature current 2, is same as field current 1. So we opted to use field current 1 since IF2 is written in terms of this. Are we seeing it, guys? Are we seeing what is happening? This gives you the power to cancel these two. It's a guys, this is a multiplication here. This is a multiplication. So these two, they can cancel each other. It's no longer there. It's no longer there. You are just left with a normal equation which you need to calculate your RD. 0.88 is equal to what? That's simply a fraction because this is 1. So 1 times this is going to remain as it is. RD over what? RD plus 0.15. So this is the same as over 1. We need to calculate RD. So you're going to perform cross multiplication. This, and multiply everything here. This multiply everything. The 0.88 multiplies RD. The 0.88 multiplies the 0.15. It multiplies everything. So it's 0.88 times RD, which is going to give us 0.88 RD. 0.88 times 0.15. That is going to give us 0.132, which is equal to, you multiply this, 1 times RD, this one, along. So this is going to give you RD. You can use that as X, it's your understanding. You need to calculate that RD. So you have to collect the terms that has got RD to one side of the equation. This is the same as 1 RD. So you can take it this side, you're going to take it to that side, it's up to you. So if I take this to the other side here, it's going to be a negative. So it will be 0.132 is equal to RD minus what? 0.88 RD, which is the same. This is same as 1. So it's 1 minus 0.88, which is going to give us 0.12 RD, which is equal to 0.132. So I need RD. I can simply divide by what? 0.12. Back to your solving of the equation. So this was going to cancel, and you have RD there. So your RD is what? From this, you have it. That was going to give you 1.1. So you're going to have 1.1 ohm. That is our question. That is the condition of your question. So you see, you have to figure out, as the question is given, you have to figure out what is it that I'm having. And from your main speed, because the main speed here formula is to be used. As we can see, we are not neglecting our main speed formula. We are not given anything about the torque here, in this case that we had, so we never had anything about the torque. So the main speed is still playing a role. But look what happened there. It can end up like that. It is not always where you have to come back to the main speed and find what is unknown. It can form an equation which you will need later on to solve anything that is required on the final condition. Considering your circuit as it is given, what type of circuit are you having there? And considering this part that we talked about of the voltage drop that is being negligible, that is not of effect, that E1 is equal to E2, and we never had any part where this was to be used. We never had any effect. So guys, we need to revise as much questions as we can, trying to see how these questions are supposed to be given is very, very important. If you consider another question that we have on this other part, they are saying It's a 200-volt DC shunt motor. It's a shunt motor that we have there, running at a speed of 1,000 revolutions per minute, draws an armature current of the useful flux per pole. This time they are giving us the useful flux. So remember the condition where the useful flux that I always talk about being proportional to the field current. So we are using the field. Where the field current was, we are just going to use the useful flux. That's the only condition, guys. So in this case, let's see how our question is given. They are saying the useful flux per pole is 55, the armature resistance. Then if the flux is suddenly reduced to, so the part of the suddenly there affects also the speed when you are given this suddenly condition. N1, it will be equal to N2. So the speed will remain suddenly, you're considering the suddenly concept. N1 will be equal to N2. Determine by how much the armature current will rise. The speed that the motor will eventually reach, assuming that the load torque remains unchanged. It's another condition. So we can see that the speed is going to change. This armature current is going to change. But we are not given a condition like what we, guys, if you, okay, see, yes, only that I removed. Now I'm showing you some other things that you're not supposed to see there. But if you check, they're not giving us a condition like what I wanted you to have previous, like all those previous questions you're given. Whatever that changed, it is because maybe there is a series resistor which was connected to the armature, or there was a parallel resistor connected which is parallel to the field, whatever that you're given. There must be a condition, as I said before. But this question, we can see there's no condition. There's nothing that we are told. So what are we going to do? Because our focus is to have original and the final. We're just going to have those diagrams, guys. No problem. So, but considering that it's a shunt motor that we have. So let's see what's going to have. So this is your original condition. It's just your normal shunt motor. Just going to have it here. All right. So let's have the part of our armature in this case. Then we, like I said, this is your original condition, this one. And we're going to need final condition. All right. So working with the circuit of the final, it is simply the same as what we had on the original in terms of the presentation, because we are not told exactly what happened, but we do know the effect of whatever that happened there. Whether we know, we are given, but we know the effect, how or what is going to happen with these circuits. That part we must know. Terminal voltage remaining as it is, the 200 volt, meaning to say also here we have got our 200 volt. The load current as it is taken from the supply. Is it going to be the same here? No. It is going to change because of the effect that happens on the armature, because the armature current here on the final will change. The effect of the change of the armature side, because the load is taken from what? The sum of these two, remember. If you add what is part of the field, even though the field, we do not even know again because of what? This consideration here that is happening. If we are told, because we do not, maybe the resistor was connected in series. What we are given is that armature current. It is running at what? The speed of 1,000 revs per minute. Same, like I said, at this sudden condition, N1 and N2 will be equal. So if you consider that, then we have your armature. Armature current 1 is the one that you're given there. Per pole, the useful flux per pole there is 55 at original condition. We've got 55 milliwebers. Armature resistance 0.25. We have it this time. Armature resistance 0.25 is given, having our P-out and so on. Armature resistance is given 0.25. This is what you were supposed to have in terms of the presentation. Like, we do not know what actually happened, but the effects are visible in terms of what? The flux reducing, the flux to being 40 milliwebers. This is what we have. So the question was now, determine, because we have all this and there are still some things that we still have to figure out, by how much the armature current will rise. By how much will the armature current, by how much armature current will rise? The armature current initially, it is 25 amperes. So definitely when they're saying it's a rise, it means it's going to increase. It will increase to a certain value, which is your armature current 2. So by how much is it going to rise? Meaning to say we are going to need the armature current 2 so that we know by how much did it increase. We are going to need armature current 2. All right. So as we do understand, so armature current 2 definitely is going to be needed. The steps, you have your diagram. From what? The main speed formula. Is the main speed formula going to work? Is it going to help us? Definitely. But before we had our main speed formula in terms of the field currents, remember you're using these ones. But this time we are given the flux. So guys, flux and this proportional. Where the field current was, use the flux this time. So it's going to be N1 flux 1. And this will be N2. Then we're going to have flux 2 like that, the useful flux. We are no longer using the field currents this time because we are given the flux. You have the flux. So know this, guys. And with this, we can simply cancel N1 and N2 because we are saying they are the same. So N1 and N2 was going to cancel. So this equation was going to be reduced into E1 over E2, which is equal to flux 1 over flux 2. This is where you are. But with this now, these ones, they're there. So we need to obtain E1. Is there anywhere where E1 can be obtained? Or can we obtain that? So that we have to determine E2. Why determining E2? Because, guys, we're talking for this armature current 2. So it has something to do with what? E2. So from the original condition, let's focus on what? On E1. Can we have that? We can have, because there we've got armature current, and so E1 can be calculated from its original condition. Calculate what? Calculate E1. So remember the back EMF, V minus armature current resistance of the armature circuit, where we just have that resistance. Yeah, this is the resistance of the armature circuit that you have there as it is. Terminal voltage, that is 200 minus. So you're going to substitute your armature current, which is 25. The resistance of the armature circuit is 0.25. You must be careful now. We just have that resistance only. So this was going to give you 193.75 volts as what? As E1. This is your E1. But now, remember we need E2. So are we going to work on the second part? No, this equation on its own, it is giving us E2 because these are there, and E1, we just calculated. So the EMF equation, this main speed formula was going to work to give us what we need, which is E2, which we'll use there to find that armature current and see there. So let's find E2. Because E1, we have it. Substitute that E1. Remember, E1, we got 193.75 over what? E2. It is equal to these. We have the magnetic flux. Okay, so here your E1, remember guys, you calculated this here. All right, then the flux they are given 1 and 2, 55 and what? And 40. So that is 55 and 40. They are in the same units. So there's no need for us to write the milliweber there. All right, so this is where you are, guys. You can calculate your E, just try to cross multiply E2 times this 55. So that's 55. E2, then the 40 is going to multiply this, which is 40 times 193.75. So divide by 55, divide by 55. That's obtaining the value of E2. So E2 was going to give us, that was going to be 140.9. It was going to be 0.90909 and so on. So this was going to just 909, guys. There's no effect there. Because we are here 3 digits after the comma. You can just fix your calculator to 3 decimal places. You have E2 from the main speed formula. E2 is there. So you're asking yourself, this E2, the need of, or why are we actually having this? Why do we need this? Because that E2 consists of armature current, remember? Just like what we had on your E1. From E2, back EMF there. E2 is equal to V minus this. We're going to have current of armature, second, the resistance, the current that we have there, armature, and the resistance of the armature circuit. If you were to use this part, okay, and this is what you want. You want the current. E2, you have it. V, we have it. I2 is the one that you want. This resistance of armature circuit, you're just going to take as it is. So guys, as you can see, this current was going to be calculated. You can make it the subject. It is up to you. You can make this the subject. If you take to this side, it becomes what? A positive. Armature current to resistance of armature circuit is equal to, already there's a V, so you're going to take the E2 to the other side. So it will be minus E2 there. Divide by the resistance of what? The resistance of the armature circuit. So that was going to give us the current there. Substituting these values, V, your terminal voltage, which is 200. So that is 200 minus E2, which we calculated from that E2 that we just calculated. It was 140.909. So this is 140.909 over the resistance of the armature circuit, which we have as the resistance of the armature. We just have the armature as we just took our diagram as it is. Like we said, we do not know the effect that actually transpired. So we're going to take this as 0.25. So that was going to give us armature current. This was going to be 236.364. To simplify this properly. This is your armature current. So meaning to say the current is now at this value from this value from this. The armature current is now at 236.36 from this value. So the question is by how much the armature current will rise, by how much? So it increased by how much? It increased by how much? So the armature current increased by the armature current increased by, we need to know now. It increased by what? That is the diff from this one to this. The difference, that is the how it increased. So it increased by what? 236.364 minus the original that it had, which was 25. Originally, this was 25 amperes. So it increased by what? The difference, which is 211.364 amps. This is the increase from where it was from this value here. If you increase it by 211.3, it will give you this value. So here they are saying by how much the armature will, right? By how much? This, it is like in terms of the rise, the armature current rose to this value. It is now at this value. Not by how much. The by how much now is it must be the difference there. If you are to answer this question properly according to how it is being asked there. By how much? That will be your difference there. Okay. So anyways, let's see. We saw that the diagrams are not going to change but we know the effects. Then B, the speed of the motor will eventually reach, assuming the load torque remains unchanged. Meaning to say, we had the first condition, original condition. We have the current that has risen to this. Now they're saying the speed that the motor will eventually reach. Remember this one, there was a sudden reduction. So what will be the eventual at the end? We are now considering another stage from this. So there are things that we have to consider there that they are simply having. So I'm just going to remove this part, guys, so that we understand what's going to happen here. Okay, all right, this one. All right, so this will be like another stage which we are now moving to from the final, from the one that we are considering as our final of this. It was the second stage. Now we have to move to another stage. This is the typical question that you're having here. So we need the speed that the motor will eventually reach, assuming the load torque remains what? Unchanged. All right. Meaning to say the torque has to play a role this time. So we are going to consider the original condition as our one. Remember, we're the stage that we used, these two that we had. This will be the last stage now of everything. So you're going to consider this as stage 3. So I'm going to use 3. From original, this will be our final, which is now stage 3. So on the stage 3, the diagrams, guys, as we saw, these ones are just going to remain as it. So what is important is from the flux that we had as our flux 2, the torque is not changed. We are going to take the flux, remember, being proportional to your field current, which is not the effect of the field current now. From our last condition that we had, that is the one that you continue with. So meaning to say, the flux that we're going to consider too from our previous is the same, which is the 40 milliwebers. That is what you're going to have on this diagram. So the part of the flux, they played a role. What else do we need? The torque being unchanged. What does it mean? In the original condition, at full load, there's a torque there. Now at stage 3, there's a torque which is also there. It remains unchanged. T1 must be equal to T3. It is unchanged. So what is going to be the speed there? Calculate the speed, considering at this stage, you're going to call it what? N3. The speed, as we used before, your main speed formula, guys, this is what we have. If it was 1 and 2, now we consider 1 and 3. 2, we passed that stage of 2. So we consider 1 and 3. So from your main speed formula, you're going to have E1 over E2 is equal to what? N1. Are we going to use the part of the flux? No. I mean the part of the field where we use this one. No. Because we have the flux. So you're going to consider the useful flux as we had. N3. This is N3. Remember, guys, we're now at the third stage. So this will be N3. N1. N3, sorry. Here we use N1. This is N3. Flux like that. At this stage, where we need to calculate. Because remember, guys, the first effect was of the sudden, the way we said N1 is equal to N2, there was no effect there on a sudden condition. That was, we are just considering stage 1, stage 2, but no effect of speed. But now there's an effect. We need to calculate this. This is the one that thing you must calculate. You must calculate this. What are we having? N1, we have flux 1 there, we are given. 3, we have E1. If you take, we calculated this E1. We calculated that E1. We have that E1 from the original. If you still remember those calculations that we made here, E1, still remember there, your E1 was. All right, let me just remove some of these guys. They will end up having so many effects. We calculated the E1. So meaning to say, we need to have E3, which you use now to calculate what? N3. So this is what we do not have. Everything is there. What we need is the speed. So can we calculate E3 from what? The E3, guys, nothing is going to change. Remember these seconds, there's no need for even you to draw that, because we saw that there's between 1 and 2. The circuit was just going to be the same as this one. In terms of the presentation, only that the armature current has changed. But in terms of the presentation, as you had on the original here, but only that armature current is not the same. This one, you to be having armature current 3. Same, this will be E3, this will be I3. So we're just gonna use that consideration of like we have that as 3. That is 3. I want you to assume that you're having a diagram which has got what? Which has got a 3. Which has got a 3. What were you going to do if here? So let me just erase here, guys. This is that you don't have confusion. I'm just saying assume, like, let's say, there's no need for us to redraw these guys, because it's the same diagram that you're going to have. Meaning to say E3, this one that we need to calculate, was going to be obtained from which formula? Just like how you calculated your E1, you are going to calculate your E3. All right, just like how you calculated your E1, you're going to try to calculate that E3. And you say E3 is equal to what? V minus what? Armature current, when I use 3, the resistance of the armature circuit, which is just that resistance that we are simply having. Remember, here we're just using the 0.25 as it is. So you're going also, you want to calculate E3 so that we can calculate the speed. In calculation of the E3, we can say that this one is missing. It's not there. We can have our voltages there, we can have this, but this one is not there. So we have to calculate this again. So you see, guys, what is missing? I3, the armature current 3 now. From where, as we are to consider the armature, that is where the part of what? The torque plays a role. Remember, armature from what? From the torque, armature current. All right. So this is what you're going to need now. From what? From the torque. Because we do understand the torque carries what? Current. So from the torque, find armature current 3. So the relationship now is just going to be having 3, 1 and 3. So as we had before, it was T1 over what? T2. Now it's going to be T1 over T3 in terms of the torque. And which formula are you going to use? Remember, there's a formula that is the useful flux. We're not going to use that of the field, knowing that the field, the flux is proportional to the field. You're just going to replace wherever the field was. Put what? Put flux. So your formula is going to be flux 1, armature current 1, flux 2. This is 3, sorry, and this is going to be armature current 3. Like this. This is the one that you need to calculate. We are told T1 and T2, they are the same. So this is simply going to cancel just like 1 over 1. They're the same. Armature current 1, we are given. These values, they're there. So you can calculate I3 from there. By substituting, this is same going to be 1 over 1 is equal to this useful flux 1 and this 3. Remember, we are there. We are given this 1. It was 55 milliwebers. This was 55. Armature current 1. We are given, it was the one that was given on the diagram. I removed that one, but if you considered your diagram properly, it was given as 25. So that was 25 over what? This flux 3 from 2 that we had, that is 40 times what? Armature current 3. So this is it, guys. You can calculate your value like this. Cross multiply, that is going to be 1 times 40 times this. 40 armature current is equal to the product of 1 and 55 and 25. You need this. So divide by what? Divide by 40. Divide by what? Divide by 40 both sides. That's obtaining the value of the armature current. So this was going to give you 34,375 amps. So this is 34,375 amps. Having this armature current, then we can have our E, which is missing. Remember the part of E here? One that you wanted to calculate here, armature current. We now calculated this. So we can now calculate our E3. So E3 is going to be equal to what? V, which is 200 minus, this one is the value that we just calculated. Now we got 34,375. This is what we got. The resistance of the armature circuit, this one, that is going to be the resistance of armature as we have it, which is the 0,25. Okay, that is the idea there. So we can calculate our E3 from this one. E3 was going to be 191,406 volts. By having this, the speed can be calculated now from your main speed formula, because this was the missing value here. We now have it. So it is now a matter of substituting everything now. The E1 that we got, the first value that we calculated, if you still remember, guys, that was 193,75 over E3. This is the value that we just calculated now. We got 191,406, the E3 that we just calculated here, guys. So you're going to substitute all those values, everything. N1, speed 1,000 initially. Originally, it was given 1,000 revs per minute. Flux there is given 55 milliwebers over what? N3 times the flux 3, which is same as flux 2, 40 milliwebers. So by doing our calculation here, we were going to calculate what? we were going to obtain, in this case, speed. Eventually, the speed that eventually will reach. Just like that. So guys, you need to revise as much questions as you can. So cross multiply here. That will be N3 times 40 times this, 193.75. Cross multiply to the other side there. We're gonna get the 1000, multiplying the 55, also multiplying the 191. Okay. Let's just try avoid these ones. Also multiplying the 191,0. That's 406. Then we're gonna divide by all these guys to obtain this N3, 193.75. Divide also this side 40 times 193.75. So definitely this was gonna cancel. N3 is there. Your speed. N3 is there, which is representing your speed. So guys, you see these calculations now, they can be like. So our final speed was going to be 1,358, comma 365. That's comma 365 revs per minute. Remember your speed in revolutions per minute. So you are going to notice a lot of questions as we are to move on. Like I said, not to miss any of these classes, it will be best that you become part of the membership so that we gonna be explaining our electrotechniques. So let's see, guys, in our next class. How it's gonna be like. We need now to work with some exam questions and see how do they ask. Yes, let's see in our next class.